So far in our calculus course, we have been applying our derivative rules to functions that have been defined explicitly. Functions that are solved for y, like y equals 5x squared minus 3x, or functions like f of x equal to sine of 2x. These are explicit functions because they are in the form of y equals or f of x equals. In this video, we're going to learn how to find a derivative for implicitly defined relations. Relationships that are not solved for y. For example, x squared plus y squared equals 1. Now, when we think about implicit differentiation, we are going to be trying to find the derivative of y with respect to x. So this notation that we've been using in class, dy dx, this is equal to, or this means, the derivative of y with respect to x. And this is important to us in this discussion because what this means is that when I'm looking for dy dx, that means that I'm taking derivatives with respect to x, which means that x is my independent variable. And whenever I have a y, that y is representing a function of x. And so what that means for us in an equation like x squared plus y squared equals 1, I'm going to take the derivative of the x squared term just like we normally would. Derivative of x squared is 2x plus, but for the y squared term, since I'm taking a derivative with respect to x, and this is a y, then I'm going to treat the y like a something in a chain rule. So we're going to say that this term is something squared, and the something is y. Now if I take the derivative of something squared, that of course is 2 times something, and then the derivative of y is dy dx. And so this is going to be equal to 2y times dy dx. So back over here, derivative of y squared is 2y dy dx. Now I show the chain rule chart here over to the side just to explain what's happening. But really, from here on out, when we're doing implicit differentiation, we're just going to remember that whenever we take a derivative of a term that involves y, we need to go ahead and apply our derivative rules like normal, but then we're going to follow that up with dy dx because we're applying the chain rule in those situations. And we need to take the derivative of everything here in this equation, so we're going to take the derivative of 1, which is 0. Okay, so now that we've taken the derivative of everything, all we need to do is solve for dy dx, because we're trying to find what dy dx is equal to. And so I'm going to subtract this 2x term to the other side. So I'm going to keep 2y dy dx equals negative 2x, and then we're going to divide by 2y. And so dy dx is equal to negative 2x divided by 2y, which of course simplifies to negative x over y. Let's look at another example. Here we have y squared equals 4x cubed plus 5x. So I have a function that almost seems like it's solved for y, but it's actually, I got y squared. We have a function on y here. And so, and sorry, excuse me, I think I called this a function. This is a relationship. This would not be a function if we graphed it. Would not pass the vertical line test. So this is a relationship, but we're going to apply implicit differentiation. I'm going to take the derivative of every term with respect to x. And so that means when I take the derivative of the y squared, I'm going to treat that y like a something, and so this becomes 2y times dy dx, applying the chain rule in that situation. Over on this side, 4x cubed, that derivative would be 12x squared, and the derivative of 5x plus 5. Last step here, I need to get dy dx by itself, so I'm going to divide by that 2y. Dy dx is equal to 12x squared plus 5 over 2y. Next example. We have x plus y cubed minus xy equals 1. So this example is going to be a little bit more complex. We've got a few more terms to work with here. We're going to start with x. The derivative of x is 1. The derivative of y cubed, again, we're going to treat that y like a something in a chain rule. So I've got 3y squared times dy dx. And now we get to this minus xy term. This term here is x times y, and that means that we need to use the product rule. Now we have a minus here in front, and the way that I like to work with the minuses is I'm going to change that to a plus and put the negative with the x, and just keep that negative with the x as I apply the product rule, just to make sure that I don't forget about it. So I've got negative x times y. That negative x is going to be my f, and the y is my g. So let's apply the product rule. Plus, the first term of the product rule is f prime times g. So f prime in this situation is going to be negative 1 times g, which is y. Now here on this term, we don't need to multiply times dy dx because we're not taking the derivative of y. We were only taking the derivative of the negative x. So that is our f prime g from the product rule. Now we're going to go on to plus g prime f. G prime would be dy dx times f, which is negative x. And again, that is our g prime f for the product rule. Now to finish out our derivative, remember we need to take a derivative of that 1 on the other side. And so the derivative here, derivative of 1 is equal to 0. Okay, so now I'm looking at 4 terms here on the left side of this equation. 2 of those terms have a dy dx and 2 of them do not. And I still want to solve for dy dx. So what we're going to do is keep those dy dx terms on this side, but we're going to move the other 2 terms that don't have dy dx, we're going to move those to the other side. So I'm having all of my dy dx terms on one side and all of my non-dy dx terms on the other side. So that 1 gets moved over, minus 1, and then the negative y, we're going to add that over, plus y. Okay, so now on the left side, I've got 2 terms. They both have dy dx, so I'm going to factor it out. So I factored that out. My other side is still the same. So now I have a dy dx that's being multiplied by 3y squared minus x, and so I can divide by that to get my dy dx by itself, to solve for dy dx. And so my answer here, my derivative, is negative 1 plus y over 3y squared minus x. Okay, I've got one last problem for you here. And this one, I'd like for you to go ahead and pause the video, copy this down, try it on your own, and then come back and check your answer. And here is our final derivative.